Hey folks, how y'all doing? We're starting section 2.5 today, which is linear transformations. So let's go ahead and begin. We're going to start with any matrix of any size, m by n matrix, so um, m rows, n columns, and we're going to create a function where we plug in a vector, and the output is the vector multiplied by a. Yeah. So the vectors that we plug in are in our n, and the output vectors are in Rm. This is called a linear transformation. Um, so all a linear transformation does is takes a vector x and multiplies it by matrix A. So let's see an example. So if this is the matrix A, then the linear transformation T of x, well, we can work out what's happening. X is some vector. The vector has to have one weight for each column in A. So since there are two columns, there are two weights in our input vector. And so we apply the column row rule, and we multiply x1 times the entry into the first column and x2 times the entries in the second column. And so we get 3x1 minus 2x2, x1 plus 2x2, and 0 plus 3x2 as the answer. We also say that this is a transformation from vectors in R2 to vectors in R3 because our input vector had only two elements in it, but our output element vector has three elements. And so this is a transformation from R2 to R3. All right. That's what it says on this slide. The input vector is in R2, the output vector is in R3. We abbreviate this by writing that the transformation converts vectors in R2 to vectors in R3. All right. Working backwards from the last example, let's figure out what matrix would generate this linear transformation. So the matrix that we're looking for has to have three columns because there are three weights. But it only gives two numbers for the answer. So produces columns that are 2 units high. With 2 entries each. So the shape of the matrix looks like this. There are 3 columns, but the columns are only 2 entries high. And by the column row rule, when we multiply this by x1, x2, x3, x1 got multiplied by a -4 and a +1. x2 got multiplied by a -1 and a +2. And x3 got multiplied by a +2 and a -1. And so the matrix that we're looking for is -4, -1, 2, 1, 2, and -1. So if we know the matrix, we can build the transformation. And if we know the transformation, we can build the matrix. We can do either of these skills algebraically, and they should not be too difficult. In order to understand what's happening geometrically, though, and not just algebraically, we're going to make use of the standard basis vectors EI. Just as a reminder, E1 is the vector 1, 0, and E2 is the vector 0, 1, Or if we're in 3 dimensions, E1 is 1, 0, 0. E2 is 0, 1, 0. And E3 is 0, 0, 1. The unit vectors in the X and the Y and possibly the Z directions. So geometrically, I want to construct a linear transformation that rotates every point in the plane counterclockwise by 90 degrees. So what I'm going to do is I'm going to, first of all, apply this transformation to the standard basis vectors. We're going to do that on the next slide here. We applied the transformation to the standard basis vectors. So this is the vector E1. It's 1 unit to the right. And then after we rotate, we get 1 unit up. And then E2 is 1 unit up. But after we rotate, we get 1 unit to the left. So that this is what happens before and after. And then again, before and after. All right. Okay, so let's fix this up. What we do is we notate what happens after the vectors have been rotated. So E1 is now in the position 0, 1, and E2 is now in the position -1 and 0. And then we put those entries into a matrix in order. So this is the transformed version of E1, and this is the transformed version of E2. And this matrix not only rotates E1 and E2 counterclockwise by 90 degrees, but in fact, it rotates every point. This rotates E1 and E2 and everything else 90 degrees counterclockwise. So for example, if we took the vector, let's say 2, -1, excuse me. All right. And we applied this matrix to that vector, 0, 1, -1, 0. Apply this to 2, -1. That's 2 times 0, 1 plus -1 times -1, 0. We get 0, 2 plus 1, 1, which is 1, 2. I'm going to plot that on the same graph, but I'm going to plot it in blue. And that is rotated 90 degrees counterclockwise from the point we started with. That's huge. That is, we can describe geometric operations on the arbitrary points in a plane just by identifying what happens to these standard basis vectors. So let's try a couple more examples, okay? So this linear transformation rotates every point in the plane counterclockwise 90 degrees. Here we are just working out what the transformation is. If we apply this to xy, we just get -y in x. This is the theorem. If Rm to Rn is a linear transformation, the columns of A identify what happens to the standard basis vectors in Rn. This is true in all cases. So let's reflect every point horizontally across the y-axis. So I want a linear transformation that might take this and reflect it horizontally over here. All right. So we do the standard vectors. E1, E4 is just 1 unit to the right. But after we rotate it, or reflect it, sorry, horizontally across the y-axis, it's pointing over here. And so the transformed version of E1 is the vector -1, 0. E2 is pointing straight up, but if we take a vector that's pointing straight up on the y-axis and we reflect it across the y-axis, it's still just pointing straight up because it's right on the axis. And so the transformed version of E2 doesn't change, it's still 0, 1. And so our matrix is -1, 0, 0, 1. And the transformed version, or the transformation of, say, xy is -1, 0, 0, 1 times xy. X gets applied to the first column, y gets applied to the second column, and so we get -xy. And that's the transformation that reflects across the y-axis. All right. Let's find the matrix for this linear transformation. I'm not giving you any numbers. I'm just giving you a diagram here. But what we can tell from this diagram is that this vector right here is E1. E1 is one of the sides of the quadrilateral, and E2 is the other side of the quadrilateral. Another thing that we know is that the origin can't move because 0 times anything is still 0, and so any linear transformation is going to take the origin still to itself. So this can't move. This is the transformed version of the origin, is still the origin. And E1 and E2 then have to be these two sides of the quadrilateral. This is now the transformed version of E1, and this is now the transformed version of E2. So our transformation has taken these two standard vectors, E1 and E2, and rotated them, but stretched out E2 by quite a bit. So it's sort of a rotate and a stretch. Well, the coordinates of the transformed version of E1 is -1. I'm sorry, +1, -1. I've got it backwards. And the transformed version of E2 is, I'll put it over here, +2, +3. And so the matrix of the transformation is 1, -1 in the first column, and 2, 3 in the second column. We always keep the columns in order. And so the transformation we want takes points x, y, and sends them to 1, -1 in the first column, 2, 3 in the second column, times x, y. By the column row rule, x gets applied to the first column and y gets applied to the second column. So we get 1x and 2y in the first row, and -1x plus 3y in the second row. And that transformation, remember, has to work everywhere in the plane. And so if you wanted to check your answer, we could check this point and see if it goes here. This point is 1, 1. If I plug in 1, 1 here, we get 1 plus 2 times 1 is 3. -1 plus 3 times 1 is 2. And this point is, in fact, the point 3, 2. And so this linear transformation does correctly work on other points in a plane and not just the points in a standard basis. All right. So let's move on. Couple of definitions. We say that a transformation is closed under addition if this equation holds, this identity holds all of the time for all vectors in Rm. So that is, no matter what x and y are, we can either add them first and then plug them into the transformation, or we can plug them into the transformation and then add the results when we're done. So that is, when we transform the sum of two vectors, we can do either operation. We can add the vectors first and then transform them, or we can transform them individually and then add them. So we get the same answer both ways. So this is a forgiving, a not fragile operation. We have seen that a matrix multiplication is fragile, that a lot of the rules that work for numbers don't work nicely for multiplication, but transformations are closed under addition, which means that we can play around with the order and it doesn't change the results. We can combine x and y together by adding and then plug them into the transformation, or you can plug them into the transformations one at a time and then add the results, and both of them get the same answer. And multiplication, we say that transformation is closed under scalar multiplication. Matrix multiplication is fragile, but scalar multiplication isn't. If we take a vector and we scale it and then transform it, we get the same answer as if we transform it and then scale the answer when we're done. We get the same answer both ways. So we can scale the vector first, or we can transform the vector and then scale it. Either one. We have a theorem, all linear transformations, all of them are closed under addition and closed under scalar multiplication. I'm going to do just a little sidebar just for a moment. To tie this into something you saw back in calculus, when you saw the derivative, you learned some crazy rules like the product rule and the quotient rule. And the chain rule. But before that, you learned something called the sum rule that you don't even think of when you think about the derivative rules. And it was just that the derivative of a sum of functions was the sum of the derivatives. That if I wanted to take the derivative of x squared plus x cubed, I could just take the derivative of x squared and then take the derivative of x cubed and add them together, and I get 2x plus 3x squared. That's an example of being closed under addition. That is, if I add first and then take the derivative, That's the same as taking the derivatives individually and then adding them together. And the other example that we had, some books call it the constant product rule. But if I know the derivative of, say, sine of x is cosine of x, then the derivative of any constant multiple, like 3 sine of x, well, that's just the same as taking the derivative of sine x and multiplying by 3. That is, I can take the derivative of the function and then put the 3 on the end afterwards. And so that's closed under scalar multiplication. Derivatives obey the same two rules that linear transformations do, which makes them compatible with each other in a way that we will leverage in differential equations. And so just sort of as a sidebar, you've seen the concepts of closed under addition, closed under scalar multiplication before, because derivatives have these properties also. All right, back to linear algebra. Let's say we have this linear transformation that converts, this is E1, and it converts E1 into this vector, it converts E2 into this vector, and it converts E3 into this vector. So then what happens to the vector 4, negative 2, 3? Well, this is 4 times E1 minus 2 times E2 plus 3 times E3. And because of being closed under addition and scalar multiplication, I can break this up and write this as 4 times the transformation of E1 minus 2 times the transformation of E2 plus 3 times the transformation of E3. And I know what those are. This is the transformation of E1, 3, negative 2, 1. And this is the transformation of E2. And this is the transformation of E3. And so when we add these together, we get 12 minus 12 plus 6, because it's negative 2 times negative 3, is 18. 18 plus 12 is 30. In the middle row, we have negative 8 plus 8 cancels, plus 6 is 6. In the bottom row, we have 4 and negative 4 plus 3, and that's 3. And that's the result that we get when we plug this in. So knowing what happens to E1 and E2 and E3, we can figure out any other vector because they're just linear combinations of E1, E2, and E3. That's why this theorem that says once you know what happens to the standard basis vectors, you know what happens to everything, works on here. For those of you copying down, I'm going to get rid of my head so you can see the rest of that line. Sorry about that. I'll move on to the next slide in a moment, but I'll let you have a minute to write things. All right, let's move on. Suppose we have two linear transformations. The transformation of transformation 1, which is given by the matrix A, and transformation 2, which is given by the matrix B. Then how can we do this associated transformation, T1 composed with E2, T2? How can we do that? Well, by the definition, T1 composed with T2 of x is T1 of T2 of x. We plug in x into T2, then we plug that answer into T1, but T2 of x is b times x, and then T1 is a times b of x. And we've seen this before. By definition, the matrix AB is the matrix that lets us eliminate the parentheses here. And we could calculate that using the column row rule. We saw that back on day 4 when we did matrix multiplication. So the composition T1 composed with T2 is just the product AB. So if these are my transformations, if this is the matrix A and this is the matrix B, and we want to compose, what happens to T1 composed with T2? Well, the first matrix is 2, 0, 1, negative 3, 3, 2, 1, 4, 5. The second matrix is 1, 4, 2, negative 1, 3, 0. We're going to apply the column row rule to this. Split this one up into columns, split this one up into rows. And so we get 2, negative 3, 1 times 1, 4. And 0, 3, 4 times 2, negative 1. And 1, 2, 5 times 3, 0. So that gets us 2, negative 3, 1 times 1. 2, negative 3, 1 times 4 is going to be 8, negative 12, 4. 0, 3, 4 times 2 is going to be 0, 6, 8. 0, 3, 4 times negative 1 is 0, negative 3, negative 4. And that's the second column. 1, 2, 5 times 3 is 3, 6, 15. And 1, 2, 5 times 0 is a column of all zeros. And when we add those together, 2 plus 0 plus 3 is 5. 8 plus 0 plus 0 is 8. Negative 3 plus 6 is 9. Negative 12 plus negative 3 is negative 15. Negative 15 plus 0 is still negative 15. And 1 plus 8 plus 15 is 24. And 4 and negative 4 and 0 is 0. And so this is the matrix of the linear transformation right here. All right. So let's look at these matrices here. Transformation A goes from as the matrix AX. The transformation S is BX. Part 1 says that we write that the transformation T takes vectors in R3 and sends them to R3. What is the correct thing for S? So S is based on matrix B, which has 2 rows and 3 columns. And so is the answer R2 to R3, or is it R3 to R2? The correct answer is R3 to R2. That is, the input requires a weight for each column. And so when I plug this in, I'm going to have to tell you 3 weights. So my input has to have but then when I plug in the weights, I'm going to get a weight times this column, plus a weight times this column, plus a weight times this column. And the answer is just going to be a vector that's only got 2 entries in it. So the output has only 2 components. So it goes from 3 dimensions down to 2 dimensions. Okay? All right. Let's move on. So let's compute T of this vector here. So that's going to be 1 times the first column, 2 times the second column, and 1 times the third column. So that's going to be 1 minus 4 plus 5 is negative 3 plus 5 is 2. And then 2 minus 2 plus, 2 plus 2 plus 0 is 4. And 4 plus 6 is 10. 10 plus 3 is 13. And so we get 2, 4, 13. We're going to save that answer because the next question I think asks about it. Compute S of V, where V is the answer from part 2. So S of 2, 4, 13. We're now using the B matrix. And we're going to apply 2 to the first column, 4 to the second column, 13 to the third column. Okay? So that's 2 times negative 2, 1, plus 4 times 3, 1, plus 13 times 2, 4. And that's the vector. Negative 4 plus 12 is 8. 8 plus 26 is 34. And then 2 plus 4 is 6. 6 plus 52 is 58. All right. So we got the answer 34 and 58. What we're going to check on the next slide, and this slide, is compute the matrix of the linear transformation S composed with T. And then we're going to verify our matrix using the answer that we got from the last part, which is 34 and 58. We'll check that out in a moment. So this is S composed with T. That's S is the transformation that uses B. T is the transformation that uses A. Then the matrix we want is going to be B times A, negative 2, 3, 2, 1, 1, 4, times the matrix 1, negative 2, 5, 2, 1, 0, 4, 3, 3. 3 columns, 3 rows. So that's negative 2, 1 times 1, negative 2, 5, plus 3, 1 times 2, 1, 0, plus 2, 4 times 4, 3, 3. All right. So negative 2, 1 times 1 is negative 2, 1. 4, 2, 4, negative 2, sorry. And negative 10, 5. Plus 3, 1 times 2 is 6, 2. 3, 1 times 1 is 3, 1. And 3, 1 times 0 is 0, 0. Plus 8, 16. 6, 12, and 6, 12. And when we add those together, we get the matrix. Let's see. Negative 2 and 6 is 4. 4 plus 8 is 12. 4 plus 3 is 7. 7 plus 6 is 13. Negative 10 plus 6 is negative 4. Then the bottom row, we get 1 plus 2 plus 16 is 19. Negative 2 plus 1 plus 12 is 11. And 5 plus 0 plus 12 is 17. All right. So we have a matrix. And the question says to verify this matrix. So I'm going to back up just for a moment to see what happened. Originally, we plugged in 1, 2, 1 into T, which is A. And then we took that answer, 2, 4, 13, and plugged it into S, which is B. The composed matrix should let me plug in the original vector 1, 2, 1 and get the answer 34, 58. So let's see what happens. If we take 12, 19, 13, 11, and negative 4, 17. I'm reading down. Times 1, 2, 1. That's 12, 19. Plus 2 times 13, 11. Plus negative 4, 17. Is 12 plus 26 is 38. 38 minus 4 is 34. 19 plus 22 is 41. 41 plus 17 is 58. And that checks. And so matrix multiplication does give me the transformation of the composition S of t. All right. That wraps things up for today. Thanks for putting up with me again. Have a great day. I will see you again next time.